So let me get started the I2CNER seminar today. So today I'm Ken Kojo from IMCE. So instead of Professor Takahara, so I will chair this talk today. And so today's talk will be given by Professor Zhiqun Lin from Georgia Institute of Technology. So let me briefly introduce him. So he got bachelor degree from Materials Chemistry, Xiamen University, maybe Amoy, and master degree from Fudan University. Then he moved to United States and he got a PhD degree from Polymer Science and Engineering, University of Massachusetts at Amherst in 2002. Actually, we overlapped from 2001 to 2002. Then he moved to Illinois, so University of Illinois at Champaign, so UIUC. He had worked as a postdoc for 2 years. Then he moved to Iowa State University. Then he had worked as an assistant professor, then and associate professor. Then he moved to Georgia Institute of Technology from 2011. So now he is full professor in Georgia Tech from 2014. Actually, he got many awards, so let me introduce some of them. So he got the Frank Padden Jr. Award in Polymer Physics from American Physical Society 2002, and he got a lot of awards from university. Then now he is a fellow of the Royal Society of Chemistry, so from 2014. So today his title of his talk is General and Robust Strategies for Monodisperse Nanoparticles and Nanorods with Unprecedented Control over Dimensions, Composition, and Architectures. So please, Jim, get started.
All right. So first of all, I would like to thank Professor Ken Kojo for kind introduction. I also like to thank Professor Takahara for kind invitation. So this is my first time coming to Japan. So I arrived on Tuesday, June 2nd. So this is my 4th day here. So I had a very good impression about Japan, not to talk about the wonderful science you guys are doing. So this is my great honor today to have so many people show up in my talk. I will be discussing general and robust strategies for monodisperse nanoparticles, nanorods, with unprecedented control over dimensions, compositions, and architectures. So before I get to that, I would like to again briefly talk about the long-term relationship with Ken. So as Ken said, we actually met at UMass Amherst in 2001. So we overlapped for 1 year, and he was in Professor Xiaolin Shu's group, doing a lot of FTIR and also doing a lot of AFM studies. And at that time, I was a student at UMass. Then he moved to University of Illinois, did his postdoc with Professor Steve Granick. But after he left, then I joined Steve Granick's group as a postdoc. So then we know each other since 2001, anyway, many years back. So here, before I get to this talk, I would like to share with you 2 slides about Georgia Tech and about School of Materials Science and Engineering. So Georgia Tech actually is located in the midtown of Atlanta. So we have about like 22,000 students, and we have the largest college of engineering in US. So Georgia Tech actually is quite close to the nearby attractions in Atlanta. So including like Centennial Olympic Park, CNN Center, and Georgia Aquarium, as well as World of Coca-Cola. So if you want to enjoy Coke, so the best place to go is Atlanta. Why? Because in the world of Coca-Cola, you have like more than 100 flavors of Coke from 6 continents in that particular place you can enjoy. So from Georgia Tech to these nearby attractions, just a few minutes driving, very close, very close. So now here in 2010, the former School of Polymer Textile Fiber Engineering, PTFE, merged with School of Materials Science and Engineering. So the new school, the new MSc program at Georgia Tech now is the largest interdisciplinary program in the world. So we established the following 9 strategic thrust areas, including polymers and macromolecules, biologically enabled and bio-inspired materials. So here you can see 15% research effort goes to nanomaterials and nano-engineered devices, and we have about 10% research on the computational design, modeling, and simulations. For functional electronic and optical materials, we have 14% research activity. We have 8% faculty working on fibers and composites. In terms of energy storage and harvesting, we have about 11%. For advanced structural materials, we have about 12% research activities going on. So the last one is multi-scale structural and chemical characterization. So this is about the research areas we are having. So at Georgia Tech, in MSc, we have about 59 faculty, 39 full-time faculty in MSc. So it is a very big program. I'm talking about the program in US in terms of the number of faculty in the department. So now let me go to talk about my research. So the outline of my talk consists of the following 2 parts. So first of all, talking about how we do the rational design and synthesis of amphiphilic and or hydrophilic nonlinear block of polymers, including nonlinear diblock and nonlinear triblock. So for example, the polyacrylic acid, block polystyrene, and polyphenolpyridine, block butyracrylate, block polystyrene. So here you can see these nonlinear block of polymers include the star-like and bottle brush-like. So all these nonlinear block of polymers, actually they have well-defined molecular architectures and molecular weight. So after that, I will move on to discuss how we utilize these nonlinear block of polymers as nanoreactor or template, if you will, to craft a large variety of functional nanocrystals, including plain, cold-shield, and hollow nanoparticles, as you can see here, as well as the plain, cold-shield nanorods and the nanotubes. So first of all, I would like to talk about how we do the rational design, how we make these amphiphilic nonlinear block of polymers. So before I get to that, one question one may ask is, because nonlinear block of polymer I'm going to discuss include the star-like block of polymer. So now the question is, why you want to study the star-like block of polymers? Well, the main feature of star-like block of polymers is they are compact structures, including smaller hydrodynamic volume and radius of gyration, and the high-density functional groups. High-density functional terminal groups, and also low solution and melt viscosity and modified thermal properties. So all these actually provide the star-like polymer with the properties of high molecular weight materials without the solution viscosity penalty of linear polymers of similar molecular weight for use in drug and gene delivery, coatings, additives, and supermolecular science. So now if you are a polymer physicist, you know star-like polymers actually possess many intriguing physical properties for many fundamental research. For example, comparing the linear chain counterpart, star-like polymer actually are more easily adsorbed at the interface as they pay a decreased entropic penalty because of the presence of multi-arms. Now, the number of segments of star-like polymers in contact with an interface is large in comparison to the linear chain of similar molecular weight, again because of multi-arms. If you work on polymer blends, so this particular polymer blends composed of the linear and star-like chains. So now you will see star-like polymer would preferentially segregate at the interface, again as they pay decreased entropic penalty. So now the question follows is, why you want to study amphiphilic star-like block of polymer? Now, before we get to that, here we know amphiphilic linear block copolymer actually can self-assemble into the polymeric micelles, right? So these polymeric micelles actually, the structure is dynamically stable, and their structure for a given system depend heavily on temperature and solvent properties, among many other parameters. Now, on the other hand, for dendrimer, we know dendrimer, this particular dendritic polymer, can readily form unimolecular micelles, right, in which the hydrophilic and hydrophobic segments are covalently connected to the dendritic core. So these unimolecular micellar-like structures are static rather than dynamic, thereby leading to the formation of monodisperse and structurally stable spherical macromolecules. Now, in theory, multi-arm amphiphilic multi-arm star-like block polymers, they can also form these unimolecular micelles. This, however, has yet to be largely explored. So in our group, what we thought is we want to study this. We want to create such unimolecular micelle-like structures based on star-like block polymer. So we recently synthesized a set of amphiphilic star-like block polymer. So the first one is this 21-arm star-like polyacrylic acid, PAA, block polystyrene, PS. So we started off by reacting beta-cyclodextran, beta-CD, which possesses 21 hydroxyl group on the surface with this small molecule, yielding this 21 bromo-beta-CD macro initiator. Then we took this macro initiator, performed atom transfer radical polymerization of terbutyl acrylate, yielding this 21-arm star-like polyterbutyl acrylate in blue. So why it is 21 arms? Because we have 21 hydroxyl groups. All these can be converted into bromine functionality, allow you to grow polymers with 21 arms. So after that, we performed the second atom transfer radical polymerization of styrene, and yielding this multi-arm star-like polyterbutyl acrylate inside and polystyrene block outside. And finally, we did the hydrolysis in acid, this trifluoroacetic acid, yielding this 21-arm star-like polyacrylic acid block polystyrene. So now the inner block is hydrophilic and outer block is hydrophobic. So it is amphiphilic in nature. So we also prepared multi-arm star-like tri-block copolymer composed of inner hydrophilic polyphenolpyridine in green and intermediate polyterbutyl acrylate block in blue and outermost hydrophobic block polystyrene in black by sequential atom transfer polymerization of phenolpyridine, terbutyl acrylate, and styrene. So after we make all these block polymer, and later on I will show you we use these block polymer, these nonlinear block polymers as nanoreactor, make a lot of inorganic structures. So in addition to this amphiphilic star-like block polymer, we also make all hydrophilic star-like block polymer. So these I will show you later as my talk goes on. So now here you may have here before I go to talk about how to make block polymer, I want to briefly mention why we pick up beta-cyclodextran, not alpha and gamma cyclodextran. So we know alpha, beta, gamma cyclodextrans, these three CDs, actually they are 6, 7, and 8 sugar ring molecules, right? They are they are cyclic oligosaccharides possessing 18, 21, and 24 hydroxyl group on the surface. So the reason we go for beta CD, not alpha and gamma CD, because of limited research funding. So here you can see beta CD actually they have very poor water solubility at room temperature, so they can be easily retrieved through crystallization. However, in contrast, alpha and gamma CD, they are readily dissolved in water. So in terms of purification, to get purified alpha and gamma CD, that actually is not easy. That increases the cost. So it is time consuming, and you also need to have chromatography technique to purify alpha and gamma CD. So these two CDs are more expensive than beta. So we go for beta CD and do the reaction. So now let me move on to talk about how we capitalize on these intriguing amphiphilic star-like polymers and as the nanoreactor to make inorganic nanostructures, including, as I said, all these, with unprecedented control over their dimensions, compositions, and architectures. So the first one is how we make plain nanoparticles. So now talking about making particles, you know there are many ways in literature, right? You can make particles, including vapor condensation, solid state processes, colloidal synthesis, soldier process, hydrothermal reaction. You can use like biomimetic synthesis approach, for example, using DNA or peptide as template. And you can also use linear copolymer micelle as template, right? So however, all these techniques, they more or less require stringent experimental condition, and some of the approach I discussed just previously in that previous slide actually cannot afford the synthesis of nanoparticle with tunable size. However, the other techniques allow you to make particle, however, the size and the shape of the particles cannot be well controlled. So more or less, these techniques are very difficult to be generalized. One technique only allows you to make one or a few particles of different kinds. And lastly, all these techniques actually requires further surface modification and functionalization of the surface of the particle with capping ligands. For example, polymers, in order to dissolve these particles in solvent, like non-polar solvent or in water for targeted applications. So driven by this motivation, we thought, why not just take the star-like polymers we made and see if we can use this unimolecular micellar-like structure to craft a large variety of nanoparticles. So in the following, I would like to demonstrate the effectiveness of our star-like polymer strategy in producing a large variety of particles by taking advantage of these unimolecular micellar-like structures of this star-like polymer. So here I already show you how we make these star-like polyacrylic acid polystyrene, right? So realize that the inner PAA block in red, it is highly hydrophilic, so it imparts the preferential interaction of the metal moiety of your precursor later on you want to add in the system with the carboxylic acid group of the PAA block. So through that particular coordination interaction, you convert your precursor into the nanoparticles by reflux reaction. So now the size of the particle, nanoparticle, actually is dictated by the length of polymer chain, PAA, right? That is the length of PDBA to start with. So this actually can be well controlled by atom transfer radical polymerization because it is a living polymerization technique. Now, the solubility of the resulting nanoparticle, you look at here, actually capped by polystyrene. So that actually renders the solubility of the resulting nanoparticle in large variety of non-polar solvents. So now because of covalent connection nature between polystyrene and polyacrylic acid, right? So they are covalently connected. So we are talking about the nanoparticles with superior long-term stability. There's no any dissociation and association of surface ligand, in this case polymers, from nanoparticle surface. So we are getting long-term stability for the resulting nanoparticles. So to demonstrate what I just said, we actually went ahead, prepared three star-like PAA block PS block polymers of different molecular weight for each. So the molecular weight of inner PAA block are 4.5, 8.4, and 16.8 K respectively. And we are looking at very monodispersed polymer because they all prepared by atom transfer radical polymerization. So if you look at the corresponding size for inner PAA block, they are 7, 11, and 16 nanometers respectively, as measured by dynamic light scattering. So now we took these three star-like block polymer and used them as the template or nanoreactor. And we do the first demonstration by adding lead titanium isopropoxide as the precursor for ferroelectric lead titanate nanoparticle. So what we got is we got 6, 10, 16 nanometer size nanoparticles. So these sites actually were templated from the star-like block polymer I just introduced. You look at this particle. Actually, the surface of the particle are permanently capped with polystyrene. So this high-resolution TM image coming from this 10 nanometer Titanate nanoparticle showing high crystallinity. So that means this particle actually is highly crystalline, prepared by templating approach. So now, later on, we try to understand why we have this particle formation. Actually, it is quite straightforward. First of all, we have this PA block, right, connected with PS block. So this PA block has carboxylic acid group, negatively charged. And this negatively charged species can react with the metal moieties in your precursor. So lead 2+ and titanium 4+ can react with this carboxylic acid group, forming intermediate compound. So this intermediate compound hydrolyzed a little bit and forming another intermediate compound. Finally, we do the condensation reaction, reflux reaction at the elevated temperature, eventually leading to the formation of that titanate nanoparticle. So this is what we proposed, the reaction going on. So now, quite intriguingly, what we found is the mixed solvent we used to do the reaction to make nanoparticle actually had profound influence on the quality of the nanoparticles we produced. So when we use DMF, dimethyl formamide, as the only solvent to do the reaction, we saw the nanoparticles with irregular size and shape produced. So however, when we add 10% benzyl alcohol, BA, benzyl alcohol in the system at DMF to benzyl alcohol 9:1 ratio, we saw the particles with the best uniformity was produced. However, if you continue to add benzyl alcohol at DMF to benzyl alcohol 5:5 ratio, you see the nanoparticle actually, again, now has reduced the regularity. Why is that? Actually, all this can be understood by considering the solubility of polymer chains in these mixed solvents. So when DMF is the only solvent used to do the reaction, we know DMF is good solvent for both inner PAA block in red and PS block in black. So we have this fully expanded polymer chain conformation. Polymer chain are fully stretched in DMF. However, when you add 10% benzyl alcohol in the system, benzyl alcohol is, we know benzyl alcohol is the long solvent for outer polystyrene block. However, it is still a good solvent for inner PAA block. So at this particular DMF to benzyl alcohol 9:1 ratio, the outer polystyrene block actually collapsed a little bit. Now you have transition from fully expanded polymer chain conformation to these more compact, structurally stable spherical macromolecules. At the same time, the loading of the precursors represented as the red dots into this well-defined compartment occupied by PAA chain increased, thereby leading to the formation of nanoparticles with markedly improved quality. Now, with the further addition of benzyl alcohol at DMF to benzyl alcohol 5:5 ratio, the outer polystyrene block now collapsed way too much because benzyl alcohol does not like PS, and PS does not like benzyl alcohol. So that make precursors having hard time to enter into to diffuse into the PAA regime to react, forming particles. Therefore, the regularity of the nanoparticle going down again. So quite interestingly, this particular nanoreactor approach based on star-like copolymer is quite general. So in addition to ferroelectric titanate nanoparticles that I just demonstrated, we can also use this particular star-like copolymer to make a large variety of nanoparticles with very good uniformity and solubility, including metallic nanoparticle, they are silver and gold nanoparticles, and ferroelectric barium titanate. Here you see magnetic iron oxide. Here, this is the N-type zinc oxide nanoparticle, N-type titanium dioxide. Here you see luminescent calcedonide. It is orange emitting in this particular size. So the last one is the P-type semiconductor cuprous oxide. The solubility of this nanoparticle actually is also very good, as the surface of the nanoparticle is intermittently, permanently capped by polystyrene chains that is originally covalently connected to the inner PAA block. So here you see all these nanoparticles, they are dissolved in toluene, and we are talking about very good long-term stability. More than 2 years, we don't see any precipitation from the solution. So now, here's a question you might want to ask. So the particles you prepared by this copolymer nanoreactor approach have as good physical properties as the particles made by other means or not? So this is the question I want to address in the following 2 slides. Give you 2 examples. So the first one is the gold nanoparticles capped by polystyrene. So here you see the plasmatic adsorption from gold nanoparticles corresponding to the particle size of 6 and 10 nanometers respectively. With the increase in particle size, we see the increase in plasmatic adsorption. So this one actually is consistent with the report in literature. Another good example to look at is the magnetic properties measurement for magnetic iron oxide nanoparticles of different sizes we prepared. So here you look at magnetic nanoparticles. So we have 6, 10, 16 nanometers magnetic nanoparticle. So here we don't see the hysteresis loop indicating they are superparamagnetic. So with the increase in particle size, we see the increase in saturation magnetization. So this is also consistent with the report in literature. So that means the particles we made by this particular linear copolymer approach is as good as those particles made by other means. So now if you are a bioengineer, so you know you want to make particles which are water-soluble, right? So you can use them for many biomedical applications. So in the following, I would like to demonstrate we can also make a water-soluble nanoparticle. So to do that, first of all, we need to do the rational design to make double hydrophilic star-like copolymer. Double hydrophilic star-like copolymer. So this particular star-like copolymer now composed of inner hydrophilic polyacylic acid and outer hydrophilic polyethylene oxide, PEO. Then you add precursors. Again, the metal moieties of your precursor can selectively react with the carboxylic acid group of PAA, forming nanoparticles. Now, this nanoparticle, because of capping of PEO, it is water-soluble. So to make this double hydrophilic star-like copolymer, so we combined one-step atom transfer radical polymerization with click reaction. So first of all, we made this multi-arm star-like polyterbutyl acrylate, now converting the terminal bromine group into azide functionality by reacting with sodium azide. And on the other hand, we prepared triple bond terminated PEO, polyethylene oxide. So by nucleophilic substitution of hydroxyl group with this triple bond, ethynyl magnesium bromide. So finally, the click reaction between azide terminated star-like PTBA and PEO proposal yielded this multi-arm star-like PTBA block PEO. Again, we hydrolyzed the inner hydrophobic PTBA block into hydrophilic PAA, yielding this double hydrophilic star-like copolymer. Do the reaction, you get the particle. Now it is water-soluble. So here are 3 examples to look at. So the first one is plasmatic gold nanoparticle, and here you see catalytic platinum nanoparticle, and this is magnetic iron oxide nanoparticles. So they all dissolved in water and can be used for biomedical applications. So now here I want to briefly do the comparison to make it clear why we want to use star-like copolymer, not linear copolymer, because many research has been done. Much research has been done to use linear copolymer as nanoreactor to make particles. So now, as I said early on, linear copolymer can form polymeric micelles, right? However, these polymeric micelles, their structure is dynamically stable, and their characteristics actually for a given system depend heavily on temperature, solvent properties, and also like pH and concentration. So a little bit variation in temperature, solvent properties, concentration, pH can destroy the uniformity of your polymeric micelle composed of linear polymer chains. So that's why this approach based on linear block polymer is limited in scope. Only nanoparticles that do not require high temperature conversion from precursors can be prepared in solution by reducing the precursors and entrapped within the block polymer micelles. And on the other hand, dendrimers, we know, have been used as a template to make zero-valent metal nanoparticles. However, talking about using dendrimers, to prepare dendrimer, actually, it requires relatively tedious multi-step reaction and purification. And the size, molecular weight, and structure of dendrimer are very difficult to control. And also, moreover, it is sterically difficult for precursors to enter the interior voids of dendrimer because highly branched exterior on the surface of dendrimer. So we are talking about the diffusivity of precursors into the interior of dendrimer is quite difficult. Thereby, oftentimes, what you will get is just nanocrystals instead of fully templated nanoparticles from dendrimer. So with that all being said, in contrast, star-like block polymer, they form unimolecular micelles. They can overcome thermodynamic instability of conventional linear block polymer micelles, thereby resulting in nearly monodisperse, structurally stable spherical macromolecules. And then they can be capitalized on as the nanoreactors to produce a lot of uniform nanoparticles. So this is what I want to do the comparison. So now here I want to move on to talk about actually this particular nanoreactor approach can also allow you to make a large variety of coaxial nanoparticles. Now we know to make a coaxial nanoparticle later on I will discuss it is quite challenging by conventional means. However, use this star-like tri-block polymer composed of innermost hydrophilic polyfluorovinylpyridine in green, intermediate hydrophobic polyterbutylacrylate in blue, and outermost hydrophobic polystyrene in black. We can make coaxial nanoparticle intermittently, permanently capped by polystyrene. So the way it works is as follows. Once we make this star-like tri-block polymer, as I discussed earlier on, we add core precursors first. So the metal moieties of your precursor actually can coordinate with pyridyl group in your P4vinylpyridine, forming core nanoparticles first. Now, this core nanoparticle surface still capped by PTBA block polystyrene. So realize that this PTBA block can be hydrolyzed into hydrophilic polyacrylic acid, PAA block. Now at this stage, you add shear precursor. So the metal moiety of your shear precursor can interact with the carboxylic acid group of PAA, forming coaxial nanoparticle. So this is the way it works. So now we know coaxial nanostructures actually are conventionally obtained by dissimilar materials epitaxy. So that requires the moderate lattice mismatch. So must be less than few percent between these two dissimilar materials. Otherwise, you won't be able to get high quality coaxial nanostructures. However, by using this templating approach, as I discussed in this slide, we can circumvent the epitaxial growth limitation. So here, let me show you one example. We are making magnetic ion oxide core capped by ferroelectric titanate shear, coaxial nanoparticle. So we made magnetic ion oxide core first by reacting magnetic ion oxide precursors with the 4-vinylpyridine group in this tri-block polymer, forming magnetic ion oxide core. As you can see, it is highly magnetic responsive. When you put magnet next to it, you see all particles get deposited on the wall. So this is the core nanoparticles. So now after that, we hydrolyzed the intermediate PTBA block into PAA, now adding the titanate shear precursor, end up with coaxial nanoparticle right here. So here, this is the Kyushu nanoparticle composed of magnetic iron oxide core capped with ferroelectric lead titanate shield. So here you see the lattice mismatch between these two crystals actually are huge. More than 40% lattice mismatch, but still can be produced by our approach. So this material actually is quite intriguing. In a sense, when you apply magnetic field, you create polarization on the shield. On the other hand, when you apply electric field, you generate magnetization in the core. So it is magnetoelectric bifunctional nanoparticle. So look at this TM image. The center of the particle actually appeared dark, coming from magnetic iron oxide, and the shield is relatively lighter, that is lead titanate. And the diameter of iron oxide core is about 6 nanometer, and the thickness of coating is about 1.5 nanometer. So now if you look at this digital image, and originally we had dark magnetic iron oxide nanoparticle solution. Once the particle is capped by lead titanate, solution became translucent. However, when you apply magnetic field, again, it became transparent. So this is the Kyushu nanoparticle. So in addition to this particular Kyushu nanoparticle, we also made the other set of Kyushu nanoparticles, including magnetic iron oxide core capped with plasmonic shield, plasmonic core capped by luminescent selenide shield, plasmonic core capped by semiconducting titanium dioxide shield. So here, after we make this Kyushu nanoparticle, we want to verify this particular approach indeed allow you to make Kyushu nanostructures. So we did the SRD measurement, take this magnetic iron oxide core capped with lead titanate shield as example. So for magnetic iron oxide core, the SRD measurement showing the signature peaks coming from iron oxide. Now, once the particle surface is capped by lead titanate shield, we see the coexistence of iron oxide and lead titanate, so indicating the success in making these Kyushu nanostructures. So again, if you want to do a lot of biological study, right, you want this Kyushu nanoparticle to be water-soluble. So to do that, now just simply replace the outer polystyrene block by polyethylene oxide. And once the surface is capped by, outermost block is polyethylene oxide, you do the similar reaction at the core precursors first. Getting core nanoparticle, then do the hydrolysis, get intermediate block situated on the core nanoparticle, converted into hydrophilic PAA, adding shear precursor, you get Kyushu nanoparticle. Now, intermittently, permanently capped by water-soluble, biocompatible polyethylene oxide on the surface. So now to make this water-soluble Kyushu nanoparticle, we have to make this star-like tri-block copolymer. So to make this, we combine two-step atom transfer radical polymerization with one-step click reaction. So first of all, we made 21-arm star-like polyphosphonapyridine block polyterbutyl acrylate by sequential atom transfer radical polymerization of phosphonapyridine and terbutyl acrylate. And on the other hand, again, we prepare this PO propargyl, triple bond terminated polyethylene oxide. Then you do the click reaction between this triple bond terminated PO and azide functionalized star-like P4VP block PTBA, end up with this star-like tri-block copolymer. So here's one example to look at. Here we have water-soluble Kyushu nanoparticle. So the inner core is magnetic, so appeared dark, and the outer gold actually is coated. So it is water-soluble. With the application of magnetic field, again, solution became transparent. So this is one good demonstration about Kyushu nanoparticle for use in biomedical applications. The magnetic iron oxide core allow you to do MRI imaging, and the plasmonic gold shield allow you to do photothermal therapy to kill cancer cells. So now, quite remarkably, in this particular nonlinear block polymer nanoreactor approach also allow you to structure direct precursors in the intermediate block, forming hollow nanoparticles. This is what I want to demonstrate in the following. So to make hollow nanoparticle, now we can, first of all, design. Here, I regard this as ABA, star-like tri-block copolymer. So the outermost and the innermost, these two blocks are the same. In this case, polystyrene, the intermediate block is polyterbutyl So they are made by sequential atom transfer radical polymerization of styrene, terbutyl and styrene. Then you convert this intermediate polyterbutyl group into polyacrylic acid, PAA, adding precursors. So now this precursor only selectively segregate into the intermediate block, get sequestered in the intermediate block, forming hollow nanoparticle. So the way I say it is hollow means only the intermediate block get converted into the inorganic nanostructure. However, you still have polymer chains encapsulated inside, as you can see here. So here's one example. Here we have hollow gold nanoparticles. So here you can see in this low resolution TM image, the center of the particle actually appeared bright, indicating it is hollow. So here you can see high resolution TM image. Here you can see the crystal lattice, indicating it is polycrystalline gold nanoparticle. So the thickness of the gold is about 3.2 nanometer, and the diameter of the hollow core is about 5.6 nanometer. Likewise, we want to make water-soluble hollow nanoparticle, again for biomedical applications. So to do that now, we recently designed star-like ABC tri-block copolymer. So the A block is PEO, water-soluble, biocompatible. The B block is polyterbutyl in blue, hydrophobic. The C block is polystyrene in black, innermost block. Again, now by combining two-step atom transfer radical polymerization with one-step click reaction. So once you have this tri-block copolymer in hand, you do the hydrolysis, convert this blue block into red block, that is hydrophilic PAA, adding precursors, you are getting hollow nanoparticle capped with PEO. So to get this star-like tri-block copolymer, we do this sequential atom transfer polymerization of styrene and terbutyl, then convert this terminal bromine group into azide functionality by reacting with sodium azide. On the other hand, again, prepare this ethanol-terminated PEO. Do the click reaction, you get this ABC star-like tri-block copolymer. So what I have shown you is we are able to make plain, cold-shear, hollow nanoparticles of different sizes, different dimensions, compositions, and architectures, right? So now, so this is what I want to show. The last slide is to talk about, in terms of hollow nanoparticle linked with PEO. You see, indeed, they are hollow, as you can see in this TM image. So hollow nanoparticle, hollow water-soluble nanoparticle actually is quite interesting. Why? Because they can be used in bioimaging, photothermal therapy, and drug delivery. So now what we have done so far is to make nanoparticles, plain, cold-shear, and hollow. So they are interesting. However, they are zero dimension. There's no any anisotropy building in the system. So we spent like 3 years to finish this project. So now we have been asking ourselves, what do you want to do in the next 5 to 10 years in terms of making inorganic nanostructures? So what we want to do is we want to do the rational design and synthesis to get one-dimensional nanostructures, including nanorods and nanotubes. Then move on to get genus-like nanoparticles and BMW logo-like nanoparticles. And finally move on to get hyperbranched and even helical-like nanostructures. Actually, all these are done by rationally designed nonlinear block copolymers. Use them as nanoreactor that allow you to make a large variety of inorganic, intriguing nanostructures for many fundamental research and also energy-related and bio-related applications. So in the following, I don't have enough time to show you the details in terms of our success in making genus nanoparticle, and we started working on BMW logo-like nanoparticle. But now in the following, let me show you some slides fairly quickly how we make these one-dimensional nanorods and nanotips. So to make them, now instead of using star-like copolymer, we designed bottle brush-like copolymer. So this bottle brush-like copolymer, just like brush, you brush your hair, having multi-arms. So these multi-arms composed of two blocks. So the innermost block is hydrophilic, the outer block is hydrophobic. That allow you to make one-dimensional plane nanorods. If each brush is tri-block copolymer, and then you can do that. You can use this bottle brush like copolymer to make core-shield nanorods. So if each arm is ABC, if each arm is ABA like tri-block copolymer, similarly like what I discussed in terms of making hollow nanoparticles, if it is bottle brush like ABA tri-block copolymer, you can use them as the nanoreactor to make nanotips. So this is what I want to briefly go over in terms of these three intriguing nanostructures. So what we want to do is to make bottle brush like copolymers. And here is the motivation, because in bottle brush like copolymer, right? Because all brushes must be connected to the polymer backbone. So they have to adopt extended polymer chain conformation because of, again, entropic penalty. All polymer chain has to be stretched along the backbone, become perpendicular to the polymer backbone. So eventually, they will adopt this cylindrical shape, right? Cylindrical conformation. They also form these unimolecular micelle-like structures, just like this cartoon shows. So once we make this bottle brush like copolymer, here I skipped the detail, and we are able to use them to make these three inorganic nanostructures. They all capped by polymer chains on the surface. So if you are talking to polymer scientists, you can say these nanostructures are nanocomposites. Why? Because these are inorganic nanoparticles. However, they are capped with polymer. So this actually is hairy nanoparticle. You can regard this as nanocomposites. But if you are talking to people who work on nanomaterials, you can say these are all nanoparticles, nanorods, nanotips. So it depends on the audience who you talk to. You can regard this differently. So what I want to say in the following is, if you take that bottle brush like copolymer and use them as template, you will be able to craft a large variety of inorganic nanorods. So the first example is the gold nanorods. Here you see we have two plasmatic adsorption, one coming from transverse adsorption, the other one is longitudinal adsorption coming from gold nanorods. We are talking about the length of 100 nanometer with the diameter of 10 nanometer. So see here you may say making gold nanorods is not interesting. Why? Because there are many reports already discussing how to make nanorods, right? So, however, the message I want to convey here is, if you can rationally design bottle brush like copolymer of similar, say, of the same dimension, you can use that bottle brush like copolymer as the nanoreactor to craft the other type of nanorods. I mean, those are the nanorods of different compositions and different compositions. So this is gold nanorods. If you switch the precursors to other materials, so this one is if you switch to up-converting materials, that is yttrium, ytterbium, and erbium precursors. So if you add these three precursors in the system, you are able to make up-converting sodium, yttrium, fluoride, ytterbium, erbium nanorods of identical dimension, because the template you are using is the same. So they actually are quite intriguing and can be used in biomedical and also energy-related application, because they can convert the near IR photons into visible. So they absorb low energy and they pump out high energy. And also, by being able to absorb near IR photon, they allow you to do a lot of bioimaging study using these particular nanorods. So here, again, by using same bottle brush like copolymer, you can make magnetic iron oxide nanorods of identical dimensions. We are talking about identical aspect ratio, identical length and diameter, but different materials. So magnetic iron oxide nanorods has not yet been demonstrated in literature in terms of making uniform nanorods for magnetic iron oxide. If you continue marching on, to use different inorganic precursors. For example, this is thermoelectric titanate nanorods. If you use titanium precursors in conjunction with tellurium elements in the system, you are able to make thermoelectric lead titanate nanorods. Here you see all these nanorods having massive side-by-side self-assembly, right? So this side-by-side self-assembly actually predominant over the head-to-tail self-assembly. Actually, we have found out a simple model to understand why we have this dominant side-by-side self-assembly over the head-to-tail assembly. So this one is luminescent selenide nanorods, and it is highly luminescent. And this, of course, selenide nanorods can also be made by solution-based reaction, which has been demonstrated in literature. But this is another way to make luminescent selenide nanorods. I guess this is my second to the last slide. So here we are talking about ferroelectric barium titanate nanorods. So again, same dimension, same aspect ratio. So this ferroelectric nanorods actually is quite interesting. Why? Because for ferroelectric materials, they have size-dependent ferroelectricity. So below which you change the system from ferroelectric to ferroelectric. So they change from tetragonal phase to cubic phase. That is for barium titanate nanoparticles. However, if you are able to make nanorods, you can investigate the aspect ratio effect. You can investigate the length effect on the ferroelectricity. That allow you to do some fundamental research. So by, again, as I said, regionally designed bottle brush like tri-block copolymer, you can make Kyushu nanorods. In this particular case, gold TiO2, plasmatic semiconducting Kyushu nanoparticle. So here you see the center of the Kyushu nanorod appeared dark. That comes from high electron density gold and coated with TiO2 relatively lighter shield. So this is Kyushu nanorod. And of course, if you can design, as I said, bottle brush like ABA tri-block copolymer, you can sequester the intermediate block, convert them into precursors in the intermediate block of bottle brush like block copolymer, make them into nanotubes. So this particular case is silicon oxide nanotubes. Silicon oxide nanotubes. We know nanotubes actually structure is quite intriguing. So you can use this, for example, silicon oxide nanotubes. You can convert silicon oxide into silicon and use this nanotubular silicon for lithium-ion battery research to accommodate volume expansion in the system. Right? So, all right, let me summarize by acknowledging my folks who have been working on this project, my postdoc and my 3 newly graduated students. Now they work in company and also doing postdoc at the university. Funding from U.S. Air Force. Let me stop here. Thank you again for your attention. And I would like to thank Ken one more time for kind introduction. Thanks.